We'll be looking at a question 21 from the June 2023 paper. This is a very nice question. It's on redox titration. Let me just check if the sound is working. One moment. Testing, testing. Hopefully it is. Anyway, in this question, it's about testing to see if a compound contains iron, and it's saying that during heavy rainwater, a fertilizer is washed into a nearby river, causing the water to be polluted with a mixture of iron 2 and iron 3 ions. The student determines the concentration of iron 2 ions by titration with potassium manganate solution. Now, this much portion of the river water are acidified. Now, we need those acidic conditions, as you can see in the equation. It's acidified with dilute sulfuric acid. Each portion is titrated with this concentration of potassium manganate until a color change is seen. First question is asking you, what is the color change that is seen at the end point of the titration? It goes from a clear solution, a colorless solution, to a pale pink, a very faint pink. Now, it's asking us to work out the volume, so the volume is used in the titration, and it wants us to work out the mean titer for the 2 marks. So the first one, the volume, final takeaway initial, 12.65. The other one I'll have to use a calculator, 25.60 minus 12.65, 12.95. And the last one, when we're doing this, we need to choose the 2 closest values. And the 2 closest values, or the most concordant results, are this one, because they're within 0.10 centimeter cubed of one another. So we're going to take the average of these 2. Now, the average of these 2, add them together, 12.65 plus 12.75, and divide by 2. That gives you 12.70. It's now asking, determine the concentration of the iron 2 ions in the river water. So we're going to need to take a bit of information from here. So, the mean titer that we use, so we need to work out the moles of MnO4 minus that was used. So remember, V times C equals the number of moles. The volume is 12.70 divided by 1,000 multiplied by concentration, which is given in the question. (3.175) times 10 to the minus 5 moles. Now, if you look at the equation, the ratio between MnO4 minus and Fe2 plus, it's a 1 to 5 ratio. 1 to 5 ratio. You can see that 5 here, and you got the 1 there. 1 to 5 ratio. So we know the moles of MnO4 minus using the titration. We need to multiply that by 5. And this will give us the moles of iron 2 plus that it reacted with. Last question is asking us to work out the moles, the last part of the question. We know that N over V is equal to C. N in this case, we've just worked out 1.5875 multiplied, so times 10 to the minus 4 moles divided by the volume. Now the volume that we used in this titration of the river water was 25 centimeters cubed. So it'll be 25 over 1,000. And that gives you 6.35 times 10 to the minus 3. Let's have a look at the mark scheme. Yep, the mark scheme supports that, all 3 marks. 1 mark for volume times concentration, 1 mark for multiplying it by 5, and 1 mark for the end concentration answer. The next question, the student modifies the experiment to determine the combined concentration of iron 2 and iron 3. The student's method is below. Add excess zinc to this volume sample of river water. Excess zinc to the river water. What will that do to the river water? We'll have a look at in a moment. The solution is warmed gently and is cooled, and the excess zinc is removed by filtration. The portion, acidify the portions, and then titrate each portion with the potassium manganate solution until a color change has occurred. Now we've done step 3. We did it. We did a redox titration calculation. This is focusing on more this question, that why have steps 1 and steps 2 taken place? And to explain what's taken place, we need to use the 3 redox systems provided and their corresponding electrode potential values. Now you see the reasons for step 1. By adding excess zinc, let's have a look at excess zinc. So we're using redox system 1 and redox system 2. You see, why is zinc added? You see the electrode potential of zinc, if you compare these 2 values, this one and this one, is more negative. Is more negative than the electrode potential of the Fe3+1. Now, what that does, because it's more negative, the zinc is going to get oxidized and the iron 3+ ions are going to get reduced. So we say there's different, you could give an equation, you can write down what's reduced, what's oxidized, you can refer to the equilibrium that's shifting in both redox system 1 and 2. But I think I prefer the very simple way of saying that zinc reduces the iron 3+. Now, yeah, these are the 2 points. For why is the excess zinc removed before the titration? You see, for this, we need to compare redox system 1 and redox system 3. Because if we do not remove the zinc, again, the zinc, highlight this, the zinc, the electrode system, the electrode potential system is more negative than the manganate redox system. And what will happen is that the manganese, the MnO4 minus, the MnO4 minus would react and oxidize the zinc. Why is that? Because the electrode potential system of the MnO4 minus is more positive than the electrode potential of Zn. And these are your reasons. Just reinforcing the basics of when you're dealing with electrode potentials, the more positive the electrode potential, the greater tendency it has to gain electrons and to reduce what it's reacting with. The more negative the electrode potential system, for example, with zinc, it has a tendency to lose electrons itself, which it gets oxidized, and in turn it will reduce what it's reacting with because it's giving off electrons. And that is the end of this question. I'll see you next time. Thank you.